What tends to happen as companies get bigger is things tend to slow down. Well, actually, they're going to speed up.
Welcome to the channel. My name is Kasim. In this video, I did a highlight of the 15 minutes most important part of the Tesla battery day, and I presented to you guys in this bite-sized 15-minute form. So hope you enjoyed the video. Let's get back into it.
Yeah. It's a video of some of what's going on in the plant.
And enabled dozens of connections into the active material through this shingled spiral you can see. With simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
Yeah, this is important to appreciate. Like basically the distance that electron has to travel, you know, is just much less. So you actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. This is a big deal.
For cylindricals to be able to get rid of the tabs dramatically simplifies winding and coating.
Yeah. And
has an awesome thermal and performance benefit. And so when we put it all together and go to our new 80 millimeter length, we get 5 times the energy with 6 times the power and enable 16% range increase.
I would say it's probably about a year before we get to the 10 gigawatt hour annualized rate with the pilot plant. And this is just a pilot plant. The actual production plants will be more on the order of maybe 200 gigawatt hours, maybe more.
So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. Wouldn't it be great if we could skip that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it? You can see it here on a benchtop. Literally powder into film. As simple as that. If you do scale it up,
yeah,
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving.
Exactly, no stoplights and traffic lights or anything. You want the highway.
I want the highway.
Yeah.
And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying.
Yeah. You sort of think about like the sort of the fundamental physics of a factory or something, like, you know, how fast are things going and what percentage of the factory volume is doing useful work. And conveyance does not count as useful work. If you break the factory down into cubic meter sections and say, is a majority of this volume doing useful work, you would be astounded at how bad most factories are. They're like maybe 2 or 3%, including our factory in Fremont. And then the other thing is how fast are things going through the factory. It's like speed and density. A factory that's moving at, say, twice the speed of another factory is equivalent to 2 factories, basically. And the company that will be successful is the company that with one factory can accomplish what other companies take 2 or 3 or 4 factories to do. So this is what we're trying to do here is say, okay, how do we, with one factory, achieve what maybe 5 or even 10 factories would normally be required to achieve? Basically, Tesla is aiming to be the best at manufacturing of any company on Earth. This is the thing that's actually most important in the long run.
86% reduction in formation investment, 75% reduction in footprint.
What this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge. You can see, like, basically we can get a terawatt hour in less space than it took to make 150 gigawatt hours. This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL. So this is 100 gigawatt hours supplemental to what we buy from suppliers. And then long term, we're expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we could do it by 2030.
And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level. What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you code it.
If you use simple silicon, it's dramatically less than even the silicon that is currently used in the batteries that are made today. And you can use a lot more of it.
Yeah, with this silicon, and the anode costs $1.20 a kilowatt hour. By leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
And when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level.
In order to scale, we really need to make sure that we're not constrained by total nickel availability. I actually spoke with the CEOs of the biggest mining companies in the world and said, please make more nickel. It's very important. And so I think they are going to make more nickel. I think we need to have a kind of a three-tiered approach to batteries. So starting with iron, that's kind of like a medium range. And then nickel manganese as sort of a medium plus intermediate, and then a high nickel for long range applications like Cybertruck and the semi.
And that's what we're proposing here with our process. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and zero wastewater. Much more scalable solution.
Yeah.
And now that we have this process, obviously we're going to go and start building our own cathode facility in North America and leveraging all of the North American resources that exist for nickel and lithium. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost.
Yeah, I mean, to be clear, cathode production would be part of the Tesla cell production plant. So it would just be raw materials coming from the mine, and from raw materials in the mine, out comes a battery. We actually got rights to a lithium clay deposit in Nevada, over 10,000 acres. And then the nature of the mining is actually, I think, also very environmentally sensitive in that we sort of take a chunk of dirt out of the ground, or remove the lithium, and then put the chunk of dirt back where it was. So it will look pretty much the same as before.
And there really is enough lithium in Nevada alone to electrify the entire U.S. fleet. And eventually, as we said at the beginning, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and industry heating, and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why. The difference in the value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. We are starting our pilot full-scale recycling production at Gigafactory Reno next quarter to continue to develop this process as our recycling returns grow. Yeah. All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level.
There's an architecture that we've been wanting to do at Tesla for a long time, and we finally figured it out. And I think it's the way that all electric cars in the future will ultimately be made. It's the right way to do things. So it starts with having a single-piece casting for the front body and the rear body. In order to do this, we commissioned the largest casting machine that has ever been made. And it's currently working just over the road at our Fremont plant. Currently making the entire rear section of the car as a single-piece, high-pressure die-cast aluminum. In order to do this, we actually had to develop our own alloy. This is a big deal for casting. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. In fact, in general, we've got a lot of advanced materials coming for Tesla, that new alloys and materials that have never existed before. The battery, for the first time, will have dual use. The battery will both have the use as an energy device and as structure. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these like supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. We have a filler that is a structural adhesive as well as flame retardant. So it effectively glues the cells to the top and bottom sheet. And this allows you to do shear transfer between the upper and lower sheet. We can actually use the steel shell case of the battery to transfer shear from the upper and lower face sheet, which makes for an incredibly stiff structure, even stiffer than a regular car. It also improves what's called the polar moment of inertia, which is that you can think of like when there's a ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You won't know why, but it just feels more agile. So 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts. Long term, in any cars that do not take this architecture will not be competitive.
So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future. In addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
So stacking it up, we're not just talking about cost or range. We've got to look at all the facets. Range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
I think it's pretty nice that investment per gigawatt hour reduction is 69%. I mean, who would have thought?
Yeah.
To be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. This really bodes well for the future and means that the long-term scaling of Tesla and the sustainable energy products that we make will be massively increased. What tends to happen as companies get bigger is things tend to slow down. Actually, they're going to speed up. I mean, long term, we want to try to replace at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year. We're confident that long term we can design and manufacture a compelling